All right. Hello, many fewer of you than yesterday. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing okay today. When I was coming to work this morning, I was taking the route that I normally take to work, and today I saw a fox on the bike path, which was unusual to see a fox. I've seen them before in my area, but it's still pretty unusual to see it. And I feel kind of conflicted about what happened after that because I kind of noticed this fox from quite a distance away because it's a fox. It's got a big bushy tail. And as I was getting closer, I could see that it was like getting ready to pounce on something. Like it's getting ready to eat breakfast. And then I got closer and closer and it ran away. And so I feel bad that I've interrupted this fox's breakfast, but at the same time, I feel like I've saved probably a gosling. Yeah. But then I also feel conflicted about that. Needless to say, it's unusual for me to see a fox in the morning, and I don't know. It's a nice little touch on the bike ride in. Let's talk about operating systems. So today, what I want you to be able to do is a couple of different things. The first is I want you to be able to identify critical sections requiring mutually exclusive access to a piece of code that will run concurrently using threads or processes. Today, we're going to be focusing on threads, but I want to be clear that what we're talking about right now can apply to processes under certain circumstances. The key thing that we're going to be looking at today is this idea that threads share an address space and they are sharing certain places or certain variables or certain heap variables or whatever. They're sharing something, and multiple different threads are trying to make changes to that same thing concurrently. This can still happen with processes. This can still happen with processes in the context of there are operating system level things that are shared between processes. One of these operating system level things that are shared between processes that is something that we're somewhat familiar with now is open file tables. An open file table and the entries in the open file table when we do fork are shared across processes. This is what enables piping for us to happen. But it can also lead to situations where we have multiple processes that are working with the same file descriptor for an actual file, kind of interfering with each other. So reading one line in one process causes the next process to read not the line it was expecting to read, but the line after the one that it was reading. So we're going to focus on this today in the context of threads, but it is possible for this to happen with processes. Once we've identified these critical sections, what I want to do is I want to stop the issue that's going to come up with this. And we're going to use a tool that's called pthread mutex lock to be able to accomplish that. Pthread mutex lock is a function that will cause threads of execution to block. And we will only allow one thread of execution at a time to begin running statements after this. So we're only going to allow one thing to go into something by calling this pthread mutex lock. And we're going to cause everybody else to just get stuck and wait until it has been released. Time permitting, related to this is that when we do use pthread mutex lock, one of the problems that we're going to introduce is we will have solved the problem that we've got with critical sections where multiple threads of execution are trying to make updates to something. But by adding locks, we're adding a set of tools that cause things to block. And as we've seen with things that block with processes, specifically pipes in this case, we can get into a state where these different concurrently executing things just get stuck, waiting for the other one to do something. As we add these locks to our threaded code, we're going to wind up in that same situation. And I want to be able to identify situations like that. It's a little bit clearer to see that this is going to happen because this is entirely within our own code now. I want to be able to identify those situations, and I want to be able to propose some solutions to fix the problem, to guarantee that it won't happen if we can say that it's possible for this thing to happen. So, reminding you of this idea of threads, Processes are what we have been doing up until this point, and these are, again, traditionally considered heavyweight mechanism for concurrency. When we do a fork, we're duplicating the entire process control block. And so it's heavyweight because we're copying everything about that process. Threads, we're adding new threads of execution to our processes. And I want to change the way that we're thinking about processes now to be that every process has a thread of execution when it starts, the main thread of execution. We can add additional threads of execution to a process by calling pthread create. And this is traditionally considered to be lightweight concurrency. And it's lightweight because all we're really doing when we think about this is adding a new context. So thinking to that struct task struct, all the way at the very bottom, there was this entry that represented the architecture specific CPU register state of this task. When we add a new thread of execution to a process, we're really just adding a new context. We're just adding a new variable that's keeping track of the register state for that particular thread of execution and a stack. So there's two real things that we're adding for threads of execution compared to entire process control blocks. And so this is what leads us to think this idea that threads are lightweight or finer grained concurrency compared to processes. Let's do a little quiz, and then I promised that today we would have some time for questions about assignment 2. So we'll do the quiz first, and then I'll have some time for questions. I'll hold this up for about 5 seconds, and then I will switch over to the Mentimeter quiz. When's the next iteration for software engineering due? Aha, okay. That explains why there are so many fewer people here today. Okay. Well, if you're listening right now, then I look forward to seeing you tomorrow. I'm going to pop over to Mentimeter here, and we will get started. So there's a couple questions about processes and threads, and then we'll take a look at some other stuff here. Yeah, okay. So absolutely, the address space is shared among threads. So that is the big primary difference that we have between threads and processes from our perspective right now. Threads are faster. I do want to call on this, not to single out the one person that's picked this, but I want to call on this idea that threads are faster. And I want to add a tiny bit of context to this idea. Threads might be faster to create. It's conceivable that they are faster to create because we're doing less work. From an abstract perspective, we're really just adding a new context and adding a new stack, as opposed to copying an entire process control block. But ultimately, once the thread or the process is started, we're just running instructions. It's just instructions underneath. And so threads are not going to cause the instructions to run any faster than processes. Threads might be faster to start, and we could do the experiment to see if it takes less time to launch 4,000 threads versus 4,000 processes. But once we get to the point of running instructions, threads and processes are going to run at about the same speed. Here's another question. All right, awesome, good. Yes, we all agree. Yes, just read and write memory. We don't need any special support anymore for interacting between these threads of execution because they all share an address space. So just read and write memory. As we observed last class, you can definitely use process stuff to do things with threads. You can call exec, you can call exit, you could call pipe inside of a thread of execution if you wanted to, and have that thread of execution communicating with threads of execution in a different process. 100% you could do that if you wanted to. But within the context of a single process, communicating among the threads that are within a single process is just read and write memory. Just add a new node to the list and then it's done. You don't have to send any complex data to that other thread of execution. This is a question I asked you a long time ago. It actually wasn't that long ago. It was only 3 weeks ago that I asked you this question. Good, yes, good. It is absolutely 3. And then the following question is adding on to that, and it's the same question that I asked you 3 weeks ago. Well, what instructions are they? And again, please forgive me for the structure of the instructions here. Mentimeter does not really make it easy to have options that are code. Awesome, yes. So we've got 3 instructions for I++. We've got to load it from main memory into a register. Then we have to change the value in the register. Then we have to put it back into main memory. So we have to copy the value from memory, update it, and then send it back into main memory. This is something that we talked about briefly at the end of last class. Okay, good, excellent, yes. Many of these statements are true. The memory that threads share, this is definitely related to the idea of a critical section. A block of code that threads share is also very much related to the idea of a critical section. A block of code that can be executed concurrently is kind of equivalent to this statement, a block of code that threads share. But the best answer here is a block of code that contains a race condition, that specifically contains a race condition among all of these threads of execution. Bodie McBoatface. Data structure, Dr. Centipede. Okay, and threads. All right, and segfault. Awesome, okay. So if a critical section is a piece of code that contains a race condition, what is a race condition? Or I should say, what is a cause of a race condition? Whoa, okay, we are all across the board here this time. All right. Okay, this is directly related to the 2 questions I had asked you again from the beginning of the course. The cause of a race condition is ultimately that statements themselves are not atomic. So when I use the word statements here, I'm thinking of high-level programming language statements. The statement that is the canonical example of a race condition between threads of execution is the ++ statement. This is not an atomic operation. It's 3 separate instructions. The new thing that we have with threads of execution is that our threads of execution might get interrupted kind of in the middle of anywhere. They're going to complete an instruction and they might get interrupted, but they're not going to complete an entire statement necessarily. Statements can be more than one instruction, and so we might get interrupted right in the middle of doing this operation. Fetching instructions, so I'm going to give some spiritual credit to fetching instructions is not atomic and instructions are not atomic. If you think way, way back to Comp 2280, where when you're thinking about instructions, you get to the point of there are different phases of execution of instructions within a single processor. Yes, we remember that a little bit? Kind of, sort of. There's this idea of a state machine where we're going to fetch the instruction and then we can start decoding the instruction, and then we have to start actually doing the instruction's action that we want to accomplish. These are all separate steps when we're executing instructions on a CPU. And so I want to give some spiritual credit to this, but kind of in the same way that when we're thinking about hard drives and writing sectors is an atomic operation, is not literally atomic. Like, we're not literally laying down 512 bytes at a time. I don't think, question mark. I don't really know how hard drives actually work, but the idea that these instructions are not atomic is not really true from our perspective as someone who's coding an operating system. So we're looking at the CPU as though it is this black box, and when I ask it to run an instruction or when it fetches an instruction from memory, it will either completely complete that instruction or it will not complete the instruction at all. So it's not going to get halfway through an instruction's execution. The last one here, addition is not atomic. Addition is an atomic operation because it is an instruction. So it will either be fully completed or it will not start at all in the first place. And here's our last question. All right, okay, so yeah, locks. We can definitely use locks for synchronization, and it makes a lot of sense for us to focus primarily on choosing locks in this context because we're talking about locks and threads right now. Condition variables are very, very closely related to the idea of locks. We're going to talk, I think, about condition variables on Monday next week to give you some preview of where we're going. But the idea of a lock is that we can allow exactly one thread of execution to enter something and everybody else will get stuck waiting. If they are allowed to enter, they will immediately enter this section that we're working with. A condition variable allows us to say that instead of wanting to immediately enter a critical section once it becomes available, I don't want to enter it immediately. I actually just want to wait. I want to wait until there's something to do. I want to wait until there's something, for example, in the queue for me to actually do something with. Read is an example of condition variable from the high-level overview when I'm trying to read from a pipe and nobody's written to it yet. I don't want to enter this critical section until there's data for me to read. So I'm going to wait around until there's data. Signals and pipes can also be used for synchronization. Reading on a pipe blocks. So I'm going to get stuck waiting for something until there's actually data for me to get. Anytime I'm blocking, I can use that as a synchronization mechanism between different concurrent units. So it might be something like a thread, or it might be something like a process. And then similarly, signals are something that we can use for synchronization, although we have to do more of the work ourselves with signals. So this is the idea that I can set a flag in my process, and then once I receive a signal, then I can start actually proceeding past this loop that I'm spinning infinitely in. But it very much makes sense for us to pick locks in this case. The Barefoot Contessa. Whoa, Bodie McBoatface comes out in the top. Congratulations to Bodie McBoatface. Are there any questions about these questions before I let you ask me questions about the assignment? We're all good? I know, and I'm delighted by it. Yeah.
I think earlier in the class you mentioned that about the open file tables, how they're pointing to the same place, but potentially when the process control block is duplicated, also the open file table is duplicated.
You're right. So I mentioned earlier that when we duplicate our process control block, that the open file table is duplicated. But remember that there's kind of like two parts to our open file table. There's the part that's in the process itself, and then there's the system level open file table. The system level open file table itself is shared among the processes that have entries in their open file table. So I'm going to actually open up this. Whoops, got caps lock on here and I don't want caps lock on. I'm going to open up this and I'm going to go way back to the beginning. This is the diagram that we were looking at when we were thinking about pipes. And I'm going to just focus on the process control block and the operating system side of things here. When we did call fork, we were definitely duplicating the open file table that's in the process's control block itself. So the entries here are going to be the same in the child process, which is this one, as they are in the parent process. But the entries that we have here are relatively, I guess they're kind of like more like pointers than they are actually containing a great deal of metadata. They're pointers to the system level open file table. And so while the actual entries for standard out and standard in have indeed been duplicated, they've been physically duplicated across both of these process control blocks, they're really just pointers to the same physical thing in the system. And in this case, the same physical thing for standard in and standard out between those processes is the terminal. When we did pipe, we were adding entries to the open file table for the parent process, but we were also creating this queue at the system level. When we duplicated the open file table, we did indeed copy all of those entries in the open file table, but both the parent and child process were pointing at the same physical object from their open file table. So there are still parts of the open file table structure overall that are going to be shared between processes, even though the table itself has been duplicated.
So if you replace, let's say, a file or standard input with a file, it's going to be replaced in the system level?
It would be replaced in the open file table itself for that process. So if I replace this, this standard input for this process with some file here, we would open that file and we would add a new entry to our open file table for that file. And then if we replace standard input with that file, what we'd be really doing is kind of changing the pointer that we have here for that. Yeah.
While keeping the other one the same.
Yeah. That makes sense?
Yeah.
Okay, awesome. Any other questions? We're good. Okay, congratulations, Bodie McBoatface. I'm going to give you some time to ask questions about assignment 2 if you have any questions. I am going to time limit this, so I'm going to set 10 minutes on my timer so we can get on with some other stuff today. Should we also duplicate the output of built-ins to log.txt or just the processes like cat? That's a good question. So the question here is in the context of the log.txt output. You can safely just duplicate the output from processes. You don't have to worry about duplicating your own output. If you want to, you're more than welcome to, but that's not something the graders are going to be, they're not going to be looking for that. Should we handle pipes for built-ins? Oh gosh, no. No, you don't have to worry about that. The pipes are only going to have, you're only going to have to worry about doing pipes between processes that you're launching. Again, if you want to, you're more than welcome to, but you don't have to do that. That's not something that I'm looking to assess on this assignment. when we do dup2 in the child, it also changes the parent's OFT. It shouldn't. It should only change the open file table for the process that you're calling dup2 in. So this is actually kind of related to what we were just looking at here. When I call dup2, the context of what I've drawn here is that we've called dup2 in the parent. But if we do this in the child instead, so we add a new entry here that points to this file in the child process, when I call dup2, what I'm doing is I'm going to overwrite the entry in the open file table for just the process that I'm working on, and it's just like the local process control block open file table as opposed to the parent. It shouldn't affect the process control block for the process that we're working on right now, as opposed to changing the one that's also in the parent. So the changes that we're making with dup2 should only affect this one. It shouldn't really make any changes to the system level thing. Are we supposed to be able to launch multiple processes in one command? Yes, and the context for that specifically is, I'm going to go over here to the assignment template, and this is a good opportunity for me to say that I've added, as requested, some additional pipeline examples. So I added them to the README for the assignment template directory. The one that I'm going to point at specifically here is the one that's called cat2 emoji, this one. When you launch this command, when you execute this pipeline, this should cause 6 processes to be started. The very first cat, this one right here, when you launch this without redirecting standard input, it should be blocked on reading standard input. It's just stuck. It's waiting for you to type stuff in on the keyboard. If you open up another terminal on the same machine, so if you're connecting to Aviary, make sure you're connecting to the same bird to be able to see this. If you open up a terminal on the same machine and you run PSA, if you run this pipeline, I would expect to see 6 copies of the cat program running all at the same time. So all the programs and all the processes should be running concurrently. There's no case where you're going to have multiple programs before the pipe symbol. So there's not going to be like cat, 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 cat with no pipes. You're not going to have to launch multiple processes that way. This is the context of having to launch multiple processes from a single command. What would you recommend approach for tackling this 4th part about pipes? So I'm going to open this up and I'm going to take a look at pipes here. I'll go back up here to where it talks about pipes. The main thing, I guess, that I think about pipes is, the main advice I would give about pipes is kind of just to tell you a little bit about the way that I approached solving this problem. And I mentioned this last class, but I'll give you a little more detail about my approach to this. The way that I approach this problem is in my shell process, for every pipe symbol here, I'm going to be calling pipe. So if there's 5 pipes, like in cat, 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 I'm going to be calling pipe 5 times in my parent process in the shell. And then once I've called pipe 5 times in the shell process, then I'm going to go through the process of launching all of these with fork and exec. And for each of these, I'm going to keep track of which one of the pipes that I've created that I should keep open in those 2 processes. So I'm calling pipe 5 times in the shell process and then calling fork. That means that every process has all pipes open initially when it gets launched. As soon as that process launches, that's when I'm going to close everything except the ones that I need. So between this process and this process, I'm going to be working with pipe 0. This is going to have the write end. This is going to have the read end. Between this process and this process, this is pipe 1. And this one is going to have the write end, and this one is going to have the read end. Between this process and this process, this is pipe 2, and so on. So I'm launching all the pipes. I'm creating all the pipes in the shell process. and then closing everything I don't need in those child processes and just leaving one pipe open between them or two pipes as appropriate for where they are in the pipeline. I'll come to you in just a second. And then in the shell process, once I finished launching everything, I close all the pipes. I don't want any right ends open. I don't want any right ends left over open after I've done that. Yes? So that's a good question. The question is, do I validate my pipeline? If I typed in CRT here instead of CAT, I'm going to blindly try to exec that. And if I'm going to blindly try to open it, and if it doesn't work, then I can't launch the rest of the pipeline. So I just stop at that point. If I try to launch a program that doesn't exist, I'm going to try to blindly launch it, and I will let the OS tell me that that doesn't exist, rather than trying to check in advance to see if this is actually a thing.
You don't have to check those commands are actually listed in the commands in the directory.
Well, you have to check if they're there to open them, but once you open them, if you have to bail out because you've tried to open it and it doesn't exist, then just bail out at that point. I wouldn't do any pre-validation on it for that purpose. Yeah. Are the make files allowed to be modified? 100% yes. Yeah, if you want to modify the make file, you're very much welcome to modify the make file. In this case, about feedback, I'm going to ask you politely to email me separately if there was a problem with the assessment here, with the way that the grader was working with your stuff. The grader shouldn't be replacing the make file that you have in your submission. So whoever you are, let me know, and I'll check it out separately. What is cat? Oh, I think that's the context here. I think that's the context here. All the programs that are in the volume that I've given you are not actual compiled code. They're just shell scripts. And I'm doing this because it's convenient for me for the differences between macOS based ARM Linux and an x86 Linux that's operating on Aviary. Naming a shell script cat and then putting this inside it says that I want bash to start, and it's going to run this as a script, and it's going to launch cat, and the $@ is just take whatever arguments were passed to the shell script and pass them to cat directly. So this $@ will expand to all the arguments that you pass to cat. In this case, cat doesn't really take a lot of meaningful arguments, but TR has the same pattern. It has the same contents in its file. So TR $@. If you do TR lowercase a to z, uppercase a to z, and then you pass that in the args array to exec, then it's going to take that args array and it's going to basically dump it there so that when it actually runs the program, it's going to take those arguments. Somebody asked me this yesterday, kind of related to this. It's not a question, but somebody asked me this yesterday, kind of related to this. So, this is my shell directory. And so I have a few different parts to this. I have a C file. It's a library that does command parsing. I have a library for my stack. I have some test programs for testing this stuff out. And then I have my shell itself. My shell itself is about 200 lines long of code. So it's not super big. It's not super big. That's largely because I've taken a lot of stuff out of the shell itself and I put it into command.c. So command.c is about 160 lines of code. This is the string processing stuff to get the commands worked out. And then my stack implementation is about 130 lines of code. So overall, for these three files and nqp shell.c, It's about 500 lines of code. So it's big, like it's not nothing, but it's not thousands of lines of code. So I realize and I know that there's lots of concepts that are involved here, and it's not just about lines of code, but I think it's achievable to see some of this through in the next couple days. Yeah. The print statements? Well, the lines of code I think is probably going to have like curly braces, you mean? Because I tend to put curly braces on their own line. Yeah, I think it probably includes curly braces here too. Yeah. Yeah.
How do we know you didn't move it all on one line?
There. It's not all on one line of code. It's not even on 5 lines of code. Here, I'll give you 6 lines of code. It's not even on 6 lines of code. Yeah. Okay. Let me go back here. I said 10 minutes. And yeah, the ones that I gave to you in the first place. Yes. No, you don't have to remove quotes. So this was kind of a question that was asked last class about quotes around high. You don't have to worry about removing quotes. Just take the literal arguments that are given to you and print them out. And I think that's it. All right, awesome. Yeah. So thank you all for that. I will have a student meeting time today after class if you have time to meet with me and you need to meet with me. I'll also have it tomorrow after class if you need to meet with me. I'll be available remotely on Friday, but I can't unfortunately be on campus for that. And then I'll also let you know that when I am finished with these Mentimeter quizzes, if you haven't seen this before, I try to put a link to them in the course webpage with the correct answer selected so that you have these without having to go to YouTube and like watch 20 minutes of videos to be able to see that. So I'll do that after class today. All right, awesome. Okay, so sticking around for questions. All right, see you later. Have a good weekend. What I want to do now is spend some time taking a look at some more multi-threaded code and starting to think about what the problem cases are with multi-threaded code. So the big problem that we have with multi-threaded code is this thing that's called a critical section. And a critical section, as we saw before, this is a block of code that contains a race condition. So this is the formal definition of what a critical section is. It's a block of code that contains a race condition. A race condition then is where we've got 2 or more different concurrent actors. And so when I say concurrent actors here, I mean either a thread of execution in a process or multiple processes that are doing non-atomic mutations. So they're making changes to something that is not going to be accomplished as it's either fully done or it's not done at all. It's going to take multiple steps to make the change that we're thinking about. To shared resources. The shared resources part here is kind of one of the most important parts to this whole statement. It has to be something that both of these concurrent actors have access to and are sharing among each other. With threads of execution, that usually means they're trying to read, make changes to, and then write the same shared structure or the same variable across multiple threads of execution. However, like I said, this can be in the context of processes with things like the system level open file table. There can be multiple processes that are trying to make changes to the same shared resource that we have here. But in the context of today's class, we're thinking primarily about threads of execution. What I want to do is I want to spend some time taking a look at some code. Some of this code is directly from the textbook, and some of this code is something that I have prepared because I wanted to make something that's a little bit more concrete than the examples that we have in the textbook, because they are hyper-contrived examples. They don't really meaningfully do anything, but I want to have some examples that will meaningfully do something. The code that we're going to be looking at today, if you want to have a smaller copy of it on your screen in front of you, I will show it on the screen so that we can look at it together. But if you want to have a smaller copy, it's in this thread management repository. I've pushed some changes up to that since yesterday's class, so if you want to follow along and you already have this, please pull it. If the code that we're looking at has a race condition, what I want to do with that race condition is to try and prevent the race condition from happening by using locks. And I want to use locks to be able to enforce mutual exclusion. What I'm trying to say here is I want to make it so that if there is a critical section, only one thread of execution will be allowed to enter that at a time. And we're going to try to place this in different places and see how it affects performance of the code that we're working with. So I want to be able to see if I can place them in the correct place to get the expected output, but I also want to be able to make sure that even after I've added this, my code still actually is fast compared to what we started with no locks. So I'm going to pop over to my terminal here, and I'm in the thread management repository here. And today we're going to be taking a look at the folder that's called critical sections. There's a bunch of different examples of code in this critical sections directory, and I want to take the time to step through each of these and see whether or not it contains a critical section, how we can fix that critical section with locks, and how the addition of locks is going to affect the performance of this code. So the very first thing I want to open, and I want to open this one first because this is our textbook example. This is the really, really basic example of race conditions and critical sections. And I want to step through this code, and then I'm going to ask you just with a quick thumbs up says, yes, this does have a critical section, or thumbs down says, no, this does not have a critical section. I'll ask you that question after we're done stepping through this code. The very first thing that I want to draw to your attention is line 5 here. On line 5, we're declaring a file scope counter variable. So this is something that's going to be shared among all of the functions that we have in this code and all of the threads of execution that we have in this code. This will be available to all of those things. We have a function here that's called thread counter. Thread counter is the function that is going to be the main entry point of the threads of execution that we're going to start. There's a loop in here that loops 1,000,000 times. And for each iteration of this loop, we are saying counter plus plus. This function doesn't use the arguments that were passed to it, and it returns null. It doesn't return anything after it's done. In the main function, I am launching 2 threads of execution here. Thread 1 and thread 2, they are both being added to the main thread of execution, and both of them are going to start executing in the function that's called thread counter. The only thing that the main thread of execution does after this is wait. Blocks for those 2 threads to finish, so it gets stuck here until both of those threads return from this function. It prints out what the value of counter is, and then it exits. So there's not a lot going on in this code. And so my question to you is, so quick thumbs up, yes, there is a critical section in this code. Thumbs down, there is not a critical section in this code. What do you think? Yeah, thumbs up all around. Yes, there is 100% a critical section in this code. I'm going to go to thread management, critical sections in the same directory. I'm going to say make dash uppercase C dot dot. I don't have a make file in this directory. The make file is in my parent directory. Uppercase C dot dot says make, please look in the parent directory for a make file. I'm going to build all of these things, and I'm going to run it. So textbook example. The expected output here is 2 million. The expected output here is 2 million. And this time it was able to get to 1.1 million, 1.0 million, 1.3, 1.1, 1.1, 1.0, 1.3. It's never going to get to 2 million here. It's never going to get to 2 million here. Once we launch these 2 processes, they're both running concurrently. On my system, they are running literally at the same time. They are running literally at the same time, and they are concurrently making changes to this variable that's called counter. The changes that we're making are not atomic. They're not atomic. So remember that this operation is a load, add, and store. When threads are executing concurrently, this is a time where we've got one thread that will have control of our processor, and it might get interrupted after any of these instructions. The thread has its own context. The thread has its own CPU context structure inside of its thread control block. So that means that things like the load instruction can execute, and it can put a value from memory onto a register. And if we're interrupted after that load and some other thread of execution gets to start executing in this loop, it will also be able to load and then add, and it might store the changes that it's made to that variable before its first thread comes back again. So I want to visualize this. So if we have thread 1 here and thread 2, they're both executing concurrently. The main thread of execution has asked for these 2 new threads to start, and they're both working at the same time. We're going to constrain ourselves and say that there's 1 CPU in this system. Just to make things easier for us, we're going to say that it's at the same time as opposed to literally at the same time. Both of these are sharing this variable that's called counter. I'm going to allocate this area as our main memory. And I'm going to hand wave and say that our main memory just has names in it like this. Initially, the value that's in main memory for this is 0. We're going to say that thread 1 is going to get to go first. It's coincidentally launched first by the main thread of execution, and we're going to say that it gets to go first. So it's going to be able to do a load of counter. And then we're going to say it gets interrupted. I'm going to play the role of the hardware timer here that's interrupting our processes and our tasks. And I'm going to say that it's interrupted at this point. So the value that it's loaded here is going to have a value of 0 for counter. At this point, thread 2 is going to be able to take over, and it's also going to load counter. It's going to get a value of 0. We'll do our add operation. And then we'll do our store. And at this point, we're going to make changes to the value of counter here. And we're going to set it to be 1 in main memory itself. And then I'm going to say that thread 2 is also interrupted here before it gets to do its next loop. And thread 1 gets to take over again. We're going to do this whole context switch thing between these 2 processes. When thread 1 takes over, the first thing it's going to do is add to its copy of what counter is. And its copy of what counter is still 0. So it's going to add 1 to counter, and it's going to then store counter. And we're going to put 1 back in main memory here. there were 2 add instructions run, but only one of them seems to have actually persisted itself to main memory here. And this is the problem that we're seeing showing up when we've got this critical section in this race condition in this case. So we're never going to get to the point of having 2 million printed out here because we're constantly going to be in the state of threads of execution are going to effectively lose that add operation that we've done here because of these 2 concurrently executing threads of execution. The solution for this is to prevent multiple threads of execution from entering our critical section. I'm going to do this. This is our critical section here. Quick thumbs up. Do we agree with this? Is this where our critical section is? What if I changed it to this? Do we agree with this? Yeah, absolutely. So I'm going to constrain this pretty tightly now. This is our critical section. It's the plus plus operation. My solution to this is going to be that if counter plus plus is not an atomic operation, load, add, store, if it's not an atomic operation, then I want to make it atomic per thread. I want one thread to do load, add, store before the next thread is even allowed to load again. I want to make sure that whatever change thread 1 makes to the counter is persisted to main memory before thread 2 is allowed to load that value from main memory. So I want threads of execution to be entering this critical section mutually exclusively. I only want one thread of execution to run counter plus plus at a time. To do that, I'm going to use a function that's called pthread mutex lock. Pthread mutex lock is 2 different parts. One is that we're going to have a lock object that's going to be used and held. I'm going to use the word held by the thread of execution that is currently doing the critical section, that's currently executing in the critical section. The other part of this is we're going to have to call a function to acquire the lock, to hold it, to be able to hold it in the first place. And then I have to call a function to release the lock. I'm giving up control of this lock because I am no longer executing code in my critical section. I'm going to add a new lock, and I'm going to add this as a file scope variable. In our case right now, our lock has to be shared among the threads. This has to be accessible by all threads that need access to this lock because we only want one thread at a time to hold the lock. Only one should be allowed to hold it at a time. So I'm going to do this, pthread mutex counter lock. And I'm going to say that this is equal to, I'm going to follow along with the example here, pthread mutex initializer. This is just a fast way for me to be able to initialize it. I would otherwise have to call pthread mutex init, and I would pass null to this attributes argument if I were doing it that way. I'm going to declare this as a file scope variable so that it's shared across all of my threads of execution, and then I'm going to initialize it at the file scope level. Once I've initialized it, I need to now insert locks, lock acquisition, lock release. And so I'm going to put it here. I'm going to say pthread mutex lock, and I'm going to pass to that a reference to counter lock. So pthread mutex lock takes an address or a pointer. I'm going to pass it the address of this lock. Only one thread of execution will be allowed to proceed past this point only one at a time. If the lock is held by a different thread, then the other threads will block. They will wait at that statement until the lock has been released by somebody else. After the plus plus operation, I'm going to release the lock. pthread mutex unlock. I want to allow other threads of execution to enter the critical section that I locked previously. So with this, the state that we're going to be in right now is that thread 1 is going to enter our loop, and it's going to acquire a lock. So I'm going to copy this whole thing. Whoops. And I'm going to paste it. I'm going to move it down here. And I'm going to fill in the blanks. We've got thread 1 and thread 2. Thread 1, when it enters our critical section here, is going to acquire a lock. It's going to lock a lock. It will load the value for counter from main memory, and it will still be interrupted. But this time when it's interrupted, thread 2 is going to take over, and it's going to try to lock the lock. It wants the lock. But that lock is held by somebody else right now. And so thread 2 is not going to be able to do any of this stuff. It's not going to be allowed to enter the critical section. It wants the lock, but it's held, so it's going to block. It's going to get stuck waiting at that point of trying to acquire the lock. Thread 1 will be allowed to take over at this point. It's going to complete doing its add operation. Whoops, I'm sorry. It's going to be able to complete doing its add operation, and it's going to put 1 into counter. And then at the very end, it is going to unlock. It's going to unlock the lock. And when it unlocks the lock, now thread 2 will be able to get into the critical section. After we've unlocked the lock, I'm going to say that thread 1 gets interrupted. And now thread 2 is able to take over, and it will be able to acquire the lock. It was blocked at that point, and it effectively just becomes unblocked and is allowed to hold the lock. So it was stuck waiting at pthread mutex lock. It will now be unblocked and just allowed to proceed with this. It will then do its own load add store. And change our counter variable to 2, and it will also unlock the lock. So adding these locks makes it so that only one thread of execution will be allowed to enter this critical section at a time. And what we've effectively done is taken these three instructions that is our plus plus operation, and we've turned this into an atomic operation. Only one thread can do it at a time. So even if it does get interrupted, nobody else is going to start trying to do this thing. I'm going to run this code. I'm going to compile it, and I'm going to run it. Make -c. I'm going to run it. And the value counter is 2 million, which is awesome. That's great. That's what we wanted it to be. I'm going to do this. I'm going to copy textbooksample.c to textbooksample with locks.c. And I'm going to quit out of Vim here, and I'm going to git checkout textbook example. I'm going to go back to the state that we were originally in. I'm going to update my make file to have textbook sample with locks. And I'll update my clean rule to have the same thing. I'm going to make -c ... And now we've got two different textbook sample implementations, one with locks and one without. So textbook sample should be back in this state of we're just going to get kind of random looking values, and textbook sample with locks will always result in 2 million. Okay, good. Yes, excellent. Textbook example with locks ends almost instantaneously. It looks like it finishes almost immediately. I'm going to use a program that's called Hyperfine. Hyperfine is a program that will run different programs and basically do benchmarks on them. It's going to calculate how long it takes to do this. It does intelligent things like it will try to warm up the benchmark environment. It's going to run it a couple times before it actually measures how long it takes for that thing to finish so that it gets loaded into memory, and it's not actually going to be including that load into memory operation in the calculation of how much time this takes. I'm going to run Hyperfine here. I'm going to zoom in, and the way that Hyperfine works is that we give it the commands that we want it to compare. So I'm going to run Hyperfine on textbook sample and textbook sample with locks. Whoops, I meant to put / here, sorry. Textbook sample without locks was about, I guess, 25% faster than doing it with locks. I'm going to ask you a question, and I'm going to have to ask you this question while I'm writing this code again, because I don't know if you noticed this, but I overwrite this example while I was hastily pressing up and enter. If I do pthread mutex lock counter lock and pthread mutex unlock counter lock, how many times am I calling pthread mutex lock? A few. I'm calling it 2 million times, and I'm calling unlock 2 million times, and that's pretty expensive. That is pretty expensive. It's less expensive than I thought it was going to be. If it's only 25% slower to run with locks in this case, that's actually better than I thought. Yeah. Oh my gosh, you were so right. It is 10 times slower. Good, thank you. Thank you for correcting me here. It is 10 times slower. We're calling lock 2 million times. We're calling lock 2 million times, and we're calling unlock 2 million times. Plus or minus 1.25. Fixating on the plus or minus. Thank you for calling me out on that. Yes, it is 10 times slower. Good, that was the point I was trying to make. Yes. it is much, much slower to try and acquire these locks 2 million times. And so I'm going to add one thing here, pthread mutex counter lock is equal to pthread mutex initializer semicolon, and that should be it. I'm going to zoom out of this. I'm going to make it. I'm going to run it to make sure that I've implemented it correctly again. Awesome. Instead of calling this 2 million times, I'm going to change this to call it twice. I'm going to copy this line, and I'm going to paste it here. I'm going to copy this line, and I'm going to paste it here. And I'm going to comment these out, because I want to have both of these in this file that I published for you. I'm going to make this. Do we agree that the output here will be correct? Without even running it, just quick yes or no, the output will be correct. Yeah. I'm going to run it, textbook sample with locks. It's still going to be 2 million. And I'm going to run Hyperfine again with textbook sample and textbook sample with locks. And textbook sample with locks is now running faster than textbook sample. I mean, 1.6 plus or minus 0.3 is like, we're getting pretty close to just like, they're approximately the same in terms of how much time it takes to run. I want you to take a look at what we've just done here, and I want you to think about this just for a moment. Thread 1's going to start. Thread 1 will get the lock. Thread 1 will complete 1 million iterations of this loop, and then it will unlock the lock. Now thread 2 will get to go and run 1 million iterations of this loop, and then unlock the lock. And so we've effectively taken this code that was running literally at the same time and just made it so that it runs sequentially, as opposed to doing this at the same time. So this solution is not great, but it does solve the problem that we had originally. This takes me then to a different example. So I'm going to quit this, unless there are any questions about this. We're all okay? Good. Okay, cool. So I'm going to quit this, and I'm going to take a look at textbook sample modified A. Textbook sample modified A takes an approach that is, my main function is still going to create these 2 threads of execution. So the main function has not really changed very much. It's still printing out the value that is a shared variable among all threads of execution in this code. The thread counter function that is launched by these threads of execution declare their own counter, they increment their own counter, and they return null. Thumbs up, thumbs down. Thumbs up says there is a critical section in this code. Thumbs down says there is no critical section in this code. Many thumbs down, many thumbs down. There is no critical section in this code. This variable, I'm going to use the words thread local. This is a stack allocated variable. And so the stack itself for each thread is distinct for each thread of execution. Every thread of execution gets its own stack. That means that this counter variable here is thread local. It is not a shared resource. It's not something that multiple threads of execution are going to try and update. We're still doing this non-atomic update operation, but they're working with different memory addresses. They're working with different locations in main memory here. Now, another question, is this even going to work? No. If I try to run this textbook sample modified A, I'll give you a second to predict the output here. But it's zero. It's zero. It's zero. No thread is actually making changes to any shared resources, and they're never giving anything back to the main function. So neither thread is actually going to accomplish any task. But they're accomplishing it twice as fast as doing it with one thread. This takes me now to textbook sample modified B. Textbook sample modified B does something similar. Our main function here is still causing two threads of execution to start. But this time we're doing some different things. The first is that in my main function, I'm declaring a counter variable here, and then I've got two pointers to counters. I'm allocating on the heap these two locations that I want to be able to store an integer, and then I'm causing these two threads of execution to start. The threads of execution themselves are going to start executing here. Each one is going to allocate enough space in the heap for an integer. It's going to set that value to 0. It's going to count it, and then it's going to return that address. My main function now is going to use this option on pthread join to accept a return value from the thread of execution. So where we had previously just been returning a null and then putting null as our second argument to pthread join, now we're accepting an argument into T1 counter and T2 counter. We're adding up the result in our main function, and we are printing that out. Yes? So just for the record here, the question was, we're doing malloc in the thread of execution and we're not freeing it. Does anything happen to allocated memory after the thread itself exits? So after it returns from this function? And the answer is nothing special happens. This is technically a leak, but this is a very short running program, and so I don't really care that much. If I were doing this for realsies, I would want to I actually wouldn't want to free it inside of this function because I'm going to use this value that I'm returning, but I would have freed it in the main function itself. But because it just exits right after that, I'm not going to do that. Yeah. So quick show of thumbs, up or down. Does this code contain a critical section? Okay, we've got some thumbs up and some thumbs down. It's a mixture. I'm going to zoom out of this, and I'm going to run it. This is textbook sample modified B. We're not locking anything. There is no critical section in this code. There is no critical section in this code because there are no race conditions in this code. In this case, what we're doing is each thread of execution is calling malloc. Thread 1 calls malloc, thread 2 calls malloc. Each of these calls to malloc are going to get a different address in the heap. They're both going to get different addresses in the heap. They're both going to operate in this loop on their own separate address in the heap, and both of them are going to return that address in the heap to the main function that's waiting for this thread to finish. The main function here is going to wait for these two threads to finish, and it's passing this kind of bizarre looking void pointer casted ampersand T1 counter to get something back from this function, the address of the pointer that I want to store the result into, and then the main function itself adds them together. And so the strategy here is, let's just give work to each of these different threads of execution and let them work on their own independent thing. And after they're done, have the main thread of execution have the responsibility of combining all of the results together. If anything is a critical section in this code, it would be line 36 here, but line 36 is not executed concurrently. It's never executed concurrently. This is always only going to be executed by the main thread of execution. And so then we get the correct result here every time, because even though they are doing load add store and being interrupted in the middle of those load add stores, they're working on different memory locations here. All right. So what we're going to do tomorrow is I want to start taking a look at lists. Plus is fine. Plus is fine, but it's pretty contrived. It's a fairly minimal example of let's just add one to this thing. More realistically, the things that we're going to want to do with threads of execution is either use data structures or make changes to data structures. And so I want to take a look at a couple of examples here that are list insertion and list traversal. List traversal is going to do multi-threaded traversal of a list, so like stepping over all the nodes that are in the list. List insertion is going to do multi-threaded insertion into a list, and we'll try to figure out where we can put locks to be able to fix those problems. So we'll take a look at that tomorrow. At this point, though, you should be able to identify critical sections. These are minimally this plus operation, and we'll expand upon this tomorrow. You should be able to write code that uses pthread mutex lock to be able to protect a critical section. And I want to generalize this a little bit too. You should be able to use a lock to protect a critical section. Pthread mutex lock is an API that you can use for this, but you should generally have this idea that a lock blocks. A lock is going to cause other threads of execution to block and prevent entry of multiple threads of execution into some critical section. That's it for today. I hope that you all have a great day. I wish you success in iteration 2 of Comp 3350 if you are hastily working on that right now, and I'll see you tomorrow. Bye, everyone.